All right, I'd like to welcome you back to section 5.2. We're going to look at the logarithms. This is what ends up being very closely related to the exponential functions. These are logarithmic. If you were wondering what that first word was there, that's logarithmic. You might remember these from Algebra 2, and you might remember they're very closely connected to the exponential functions. So much so that we call them inverses of one another. All right, so let's take a look at a few things. So first of all, the definition of a logarithm, and we actually base our definition off of the exponential functions. So just a couple of quick statements here. X has to be bigger than 0. A has to be bigger than 0 but not equal to 1. And this is our statement right here. This is the big one. This is the new one for us today. The y equals log base A of x. Notice I said the word base. So if I said this is log base 2 of x. And this is not log 2x. That doesn't make log 2x looks like this, where everything is on the same line. All right, so it's not log 2x, it's log base 2 of x, or in this case, log base A of x. And something I'm going to do right here is kind of show you something. If I'm writing the logarithm down, if I wanted, if I wanted log base 2 of x, what I need to point out is this 2 is what we call a subscript. Just like if I said x squared, the 2 is a superscript. It's above the x. Here I'm saying the 2 is below the line. It's a subscript for log, and the x is not a part of the 2. It's actually log base 2 of something. And in this case, it's of x. So these 2 and this x don't have anything to do with each other. This is the log base 2. All right, just as we had 2 to the power of x, right? This x is on the exponent of the 2. All right, so here's how we compare these things. Y is equal to the log base A of x if and only if you can write it like this. A to the power of y equals x. So notice it's A to the power of y, notice we go across the equal sign, equals x. And there's things we can do with this. One of the things is where in this particular statement here, you would actually be asked, hey, what is the log base 2 of 32? Well, the thing is you don't know what that is, right? And you would say, oh, 2 to the x equals 32. And you could do some quick math and figure out that the x is equal to 5. So that means the log base 2 of 32 equals 5 because I can write this statement, 2 to the 5th power equals 32. So notice here, 2 to the 5th power equals 32. And it's the exact same thing if I said, hey, the square root of 36 is equal to 6 because 6 squared equals 36. It's the same idea. The square and the square root are inverses of one another. We can rewrite it. We can rewrite this as an x or a this is a radical equation. This is an exponential equation. All right. So let's take a look. So here I just said something silly, right? Logarithms and exponentials play very together nicely. So if I wanted to evaluate these things, log base 3 of 81, I don't know what it equals. So I want to say, okay, 3 to what power equals 81? And you could do some simple, just plug things into your calculator. 3 times 3 times 3 times 3 times 3 until you find 81. And you'll actually find that x is 4. Because 3 to the 4th power is 81. Well, same idea here. Things get a little bit more challenging, obviously. This is saying 4 to what power equals 2. And I hope you're thinking hard about this. 4 to the x power equals 2. You might not know this one, but you do know that the square root of 4 equals 2. And we know that the square root can be written as an exponent of 1/2. Because this right here is saying 4 to the 1/2 power equals 2. Okay, what about log base 3 of 1? I don't know what this is equal to. So I say, okay, 3 to what power equals 1? And I hope you know any number to the same exponent is always 1, and that same exponent is always 0. 3 to the 0 power is 1. A couple more here. What about log base 2 of 2? So 2 to what power equals 2? Well, that should obviously be 1. So log base 2 of 2 is equal to 1. What about log base 10 of 0.01? So 10 to what power is equal to 0.01? Well, that's a pretty good question because this doesn't really seem like it's got anything in common. But 0.01 is actually 1 over 100. Well, 1 over 100 could be written as 1 over 10 squared. Well, I know how to get rid of this fraction, too. This fraction tells me I can just make this a negative exponent. So 0.01 is actually 10 to the negative 2. And you'll notice if the bases are the same, the exponents obviously have to be the same. So this is negative 2. All right, and actually three of these the last three statements here actually come up in our properties. Very important properties here. The first of which being log base A. Doesn't matter what base you're dealing with. It could be a billion, it could be a half, whatever. Log base A of 1 is always equal to 0 because anything to the 0 power is always equal to 1. Likewise, if you take log base A of A, if you take the log base A of itself, it's equal to 1 because A to the first power is equal to A. And the next two are kind of tricky properties here, kind of. The first part of property 3 says log base A of A to the x power is x. And we could deal with the same thing. This A, down below, A to the power of x is equal to A to the power of x. That tells you x is x. It's kind of a weird statement. But what I want you to notice here is they kind of cancel each other out. You can think about canceling. So if I said, hey, what is the log base 3 of 3 to the 10th? Oh, that's 10 because this property tells me I can cancel those 3's. Or in the other version, exponential base A and log base A cancel each other out in the other direction. So I could say, let's get rid of this for a second here. If I said 3 to the power of log base 3 of 10 is also equal to 10. So notice the exponential base 3 and the logarithmic base 3, they cancel each other out. Now these are pretty tricky properties to deal with. These two, well, the bottom one especially. Number 4 here, this is almost kind of an obvious statement. If the log base A of x is equal to log base A of y, that's got to tell me that x equals y. Because they're the same bases. It's like the square root of x equals the square root of 4. X better be 4. Right? Same idea. All right. Moving right along here, let's solve for x. Not a lot of hard solving in this particular lesson, but we can still solve for x. Very easy one. log base 2 of x is equal to log base 2 of 3. Well, we just went over this. If the log base 2 and a log base 2 have something on the insides, they have to be equal, so x is 3. Same kind of idea if I was to ask you the log base 2 of x plus 1 equals the log base 2 of 2x minus 3. I could say x plus 1 equals 2x minus 3. I could get x equals to 4. No big deal. However, there comes a problem if I was to say log base 2 of x is equal to log base 3 of 7. You can't just say x equals 7 here. Actually, for us right now, there's no way to solve this problem. There will be later, but right now there's no way to solve this problem, because the bases are not the same. What about the next one? Log base 4 of 4 equals x. Well, some of you guys are thinking these are way too easy, and some of them are. For right now, you're only allowed easy questions to be able to solve for x. Later, we'll get the hard ones. All right? Well, in this case, my property says if I use the base and the number, it's just 1. Log base 4 of 4 is just 1. All right. The little basic things of logarithms aren't too bad for now, but let's get looking at graphing. And I kind of want to think about inverses. And you might remember that inverses, you have to do a little swap x and y. Hopefully you remember that. We're going to keep that in the back of our mind for now. And what I want to do is I want to look at log base 2 of x. So you might recall that we started the last video with y equals 2 to the x power. And we created a table of values, and we went something like this, -2, -1, 0, 1, and 2. And we got, what did we get? 1 over 4, 1 over 2, 1, 2, and 4. Now, here's what's nice about these two things being inverses. Notice it's log base 2 and exponential base 2. Because these two things are inverses of one another, their tables are going to look very similar, and it has to do with swapping x and y. Well, in this case, I can take these values and I can swap x and y, which means I get 1/4, 1/2, 1, 2, and 4. And I get -2, -1, 0, 1, and 2. And that's actually the table that we're going to use to graph the logarithm. Got to go out to 4 here. And got to go up to 2. And down to -2. And what you will notice here is there will be a vertical asymptote this time at 0. So there's a vertical asymptote there. And we go to graph this, and we just plot our dots. 1, 0. 2, 1. 4, 2. Half, fourth. And do the best you can. Connect your dots. Or make your dots bigger so they touch. And this is the log base 2 of x. And there's all sorts of stuff we can do with this. But you notice that it actually comes from looking at the y equals 2 to the x, looking at its points, and just reflecting, swapping x and y. So let's go ahead and look at a different one. Oops. Come on. All right. So let's look at log base 3 of x. Let's do the same kind of thing we just did. This has an inverse of y equals 3 to the x power. If we think about a table for this, using the same values, -2, -1, 0, 1, and 2, just like we did for exponentials, I could get these numbers 1 over 9, 1 over 3, 1, 3, and 9. Well, then in order to just graph the log base 3 of x, I can say, all right, so swapping x and y, I get 1/9, 1/3, 1, 3, and 9, and I get -2, -1, 0, 1, and 2. And I can just go ahead and graph that. And you'll notice it actually looks a lot like the other, or not a 3, just like the other graph. Oh, I did it again. 2. There we go. -2. Here's the problem. That has to go to 9. So 2, 4, 6, 8, 9-ish, whatever. So you still have your asymptote at 0 because we haven't shifted left or right at all. And we're going to get our point. Oh, let's not use blue because that's what we were using a second ago. Let's use yellow. All right, so here we go. At 1, 0, 2, 4, so 3, 1. Oh, yellow doesn't work. And 9, 2. And we go back. Here's a 3rd, and here's a 9th. And you remember things get really close to that asymptote very quickly. All right, there we go. That's log base 3 of x. So one thing I haven't mentioned here is things about domain. Domain here is my x values, and notice here it's all positive numbers. So it's 0 to infinity, where in this case the range is all real numbers. And the same thing goes for log base 3 of x. Because I haven't moved things left or right, the domain is the same and the range is the same. And actually for all logarithms, the range will always be all real numbers. The domain is what changes, and the domain depends on a left or right shift. I do want to throw this one in there just because I want to make sure we understand what's going on here. We're going to look at y equals 0.5 to the x power. You guys might remember this is 1/2 to the x. We looked at something like this. This was the decay model from last section. -2, -1, 0, 1, and 2. -2 actually became a 4. This is a 2, a 1, a 1/2, and a 1/4. And we're just going to do the same thing as before. We're going to swap x and y. So 4, 2, 1, 1/2, 4th, and -2, -1, 0, 1, and 2. And I really want to just kind of point out the different shape of the graph and what happens here. So 1, 2, 3, and 4, and a 1, 2, and a 1, 2. We go to plug in our points. We still get that 1, 0. You notice that 1, 0 comes up all the time. Sorry, I forgot my asymptote there. The asymptote stays. Notice here how this is different than before. 4, -2, or yeah, 4, -2, 2, -1. And here's where we go to half and whatever. So you notice instead of growing over time, it actually shrinks over time. It actually goes negative in this case. But you'll notice the domain is still the same thing. All numbers bigger than 0. And the range is still all real numbers because this infinitely goes up and this infinitely goes down. What about something like this? This is, well, we've already done this sort of stuff before. This is just taking this function. So notice log base 2 of x, and we got log base 2 of x minus 1. This, the minus 1, just means right 1 unit. So we can take everything that we had from the previous graph and move everything right 1 unit. So my asymptote is then going to be at 1. 2, 3, 4, and 5. I'm going to get these dots here. And notice the graph is exactly the same, only shifted to the right 1 unit. All right, so you can kind of pay attention to that. That's a right 1 unit. And there's all sorts of things we can do here. You might note that I put these two particular functions on here for a reason, because I need you to make sure you understand that the parentheses here says it's a right 1 unit, whereas this one says down 1 unit. Oh, and in this particular case, for log base 2 of x minus 1, the domain has now changed. It's not 0 to infinity, it's actually starting at 1 to infinity, and notice it changes because of the 1 here. It moved to the right 1 unit. All right, and then I just kind of wanted to throw everything in here. Notice I'm using the log base 2 just as an example. But we can still think about what all this stuff's going to do. This is up 3 units. This is left 1 unit. And don't forget the minus here. The minus is a reflection over the x-axis. All right, so important little things there you got to pay attention to. And most of you are kind of catching on to this whole transformation thing, which is a good thing. All right, let's look at a couple of logarithms that show up most often, especially when we're doing solving equations and stuff in the real world. We kind of just basically try to use these two logarithms all the time, and more natural log than the other. All right, so first of all, the common log is log base 10. And we write log base 10 without the 10 underneath it. So you notice you could write it as log base 10 of x, or you could leave it out. You don't have to write the 10. If you don't write the 10, that means I assume it is a 10. And this is actually the one that's found on your calculator. You can find that down towards the bottom left if you're using a graphing calculator. It's down towards the bottom left. It's just LOG. So if you wanted to do this on your calculator, you could. If you wanted to do the log of 2 on your calculator, you can get some random decimal. But if you wanted to do log base 3 of 2 on your calculator, we got to wait another section or so before I teach you guys how to do this. So this one you can't do on your calculator. This one you can, because the log is base 10. And the other one is the natural logarithm. This is log base e. So notice the e shows back up again. And this is called the ln. This is in capital letters, by the way, ln of x. So we use ln to represent the natural logarithm. It's written backwards. I know, I don't know why either. I do. It's the Latin. It's Logarithmic Naturale or something like that. But it means natural log. It's log base e. And more often in calculus, this is going to be used. And in the real world, when we're solving equations, this is going to be used. And this one is also found on your calculator. It's also in the same spot down underneath the LOG. And you could do stuff on your calculator like, oops, not x. You could do ln of 3. You could do ln of 1 million. Whatever you wanted to do. You could not do ln of negative 3, though. You could try this, and it doesn't work because it's not in the domain. Now, the natural log has the same properties, only now we get to deal with the letter E again. So the natural log properties, first one, same as normal. And ln of 1 is equal to 0 because e to the 0 power is equal to 1, right? Because this is base e. ln of e is equal to 1 because e to the first power is e. So you'll notice these properties are same as the other properties. They're just rewritten as using the natural log. So this property is the same thing. Natural log of e to the x is equal to x. They cancel. And e to the power of ln of x is equal to x again because they cancel. And lastly, if you have two natural logs equal to each other, the things on the inside have to be equal. All right, so there's all of our properties. The natural log gets graphed the same way, only we have to look at the graph of e to the x. And we did this a little bit, I believe, in the last video. But you'll notice that it actually graphs almost the exact same way. It looks exactly like all of the other functions. Here's a 1. And we get the asymptote. It looks exactly like all of the other functions. They're not too difficult. And all the properties still apply. All the transformations still apply. All right, here's your assignment. It's a little bit lengthy for the do to me piece, but it's because there's a lot of going back and forth between a logarithm and an exponential. Something like 2 to the x power equals 7. I could write this as an exponential equation. Or sorry, this is an exponential equation. I could write it as a logarithm by saying log base 2, because it's base 2 here, go across the equal sign for the 7, and it's equal to the exponent. Or I could say, hey, write this as an exponential equation. Well, it would just be 3 to the x equals 5. Obviously, you can't solve that yet, but we will. All right, there you go. See you guys tomorrow.